we're continuing with the 1.9 material, and we're going to apply Theorem 12. This is what you need to be able to do. You need to be able to apply Theorem 12 to do exercises like what we're about to do right now. So Theorem 12 says that a linear transformation is onto if and only if the columns of A span Rm. And we know, I think it was Theorem 4 back in 1.4, that's equivalent to showing that every row of A has a pivot position. So the pivot position statement is like the easier way to work with this from a matrix. And part B, T is 1 to 1 if and only if the columns of A are linearly independent. Okay, so now let's go ahead and do these exercises. So we're going back to in the first exercise, we're going back to the example I marked as A in a box in both the onto and one-to-one discussion. It's a linear transformation defined by this matrix, and the matrix is 2 by 3, so the linear transformation is from R3 to R2. And so the first question is T onto, and again we're gonna answer this question by applying our theorem. The question is, do the columns of A span R2, the codomain space? And another way to answer that is there a pivot in every row? And that was our theorem 4 in section 1.4, if you're wondering, if you're like, when did we figure that out? And of course, in my example, this is already in reduced form. We can see the pivots, and we can see there is a pivot in every row. So therefore, T is onto. Now we also have to ask the question, is T 1 to 1? And according to Theorem 12, we're asking ourselves, are the columns of A linearly independent? Well, the columns of A are 1, 0, 0, 1, and 0, 0. We have one of the columns is a 0 vector. And we know any set containing the 0 vector is linearly dependent. Thus, the columns of A are dependent, not independent, and therefore T is not 1 to 1. So I hope that, the conclusion here is that it's really easy applying Theorem 12 to determine whether this linear transformation with matrix A is onto or one-to-one. It is onto, it's not one-to-one. Now let's move on to the next exercise. And what we're going to do is the same thing with the other example we looked at that I marked with a B in a box in the earlier discussion. So here the matrix, I was still calling the matrix A though, so it's a different matrix, this 1 0 0 1 0 0 1 1. And so here our linear transformation T is still defined by multiplication by A. A is 4 by 2, so this linear transformation is from R2 to R4. And so let's say is T onto. Okay. And again, the shortcut way to determine this is there a pivot in every row? And we can see here, I guess, well, we don't even have to reduce it. We don't even have to think about it any further. There can be, at most, 2 pivots, because you can only have 1 pivot per column, but we have 4 rows. So there must be rows with no pivot, and so therefore T is not onto. Is T one-to-one? So we're going to ask ourselves, are the columns of T linearly independent? Well, are the columns of A, I should have said, columns of our matrix A linearly independent? Well, we got 2 columns. We got 1 0 0 1. And we have 0 1 0 1. Now, it can take a little bit of work sometimes to determine if a set of vectors is linearly independent, but here we have 2 vectors, and we have our shortcut that we can apply when we have just 2 vectors. They are, I can just see here, they are not scalar multiples of each other. Or you could just say one is not the scalar multiple of the other. So by our shortcut, they are thus linearly independent. That was from 1.7, where we made the observation that 2 vectors that are not scalar multiples of each other are going to be independent, and therefore T is one-to-one. So in this example, I can almost squeeze everything on there. The linear transformation turned out to be not onto, but it was one-to-one by applying theorem 12. Now we're just about through with this 1.9 handout. So these 2 exercises are really, you know, they're really straightforward once you see how to do them, but it's really important to know how to apply theorem 12 in these situations. The last page of the handout is the actual proof of Theorem 12. I'm not going to go through that with you. I hope you read this over on your own, because I do try to write these up in a way that they're readable and clear, and so, but that's just extra. If you're not going to be responsible for reproducing this proof or pulling out any steps from it, but I do hope you spend some time trying to see the logic involved. And that's the end of 1.9.